Okay, so picking up where we left off, we're talking about the class equation here. So I wrote this out in kind of a funny way, but just to review, we're talking about a finite group G, and we're saying that its size is the size of its center plus the size of this other term, which is the size of G over the size of the centralizer of G, where this sum ranges over the distinct conjugacy classes in the G, subtract the center. So recall that the conjugacy, so let's recall that so the centralizer are all of the things which are central with respect to little g. So maybe it's okay for me to kind of complement this with a little bit more writing. So let's recall, I defined these in the last lecture, but let's recall that cent g is h and g such that hg is gh, right? So this is the stabilizer of little g. So this is exactly the stabilizer of little g under the conjugacy, under the action by conjugation, right? So it's exactly h g h inverse is g. This equation also reads h g h inverse is g. So that's the stabilizer. And so this g mod cent g is exactly the size of an orbit. So if you work it out, this is just saying that g is the size of g is the sum over the size of the different orbits under the action, right? And that is obvious because the orbits break the set up, and the disjoint union of the orbits is exactly the set under any group action. So when I talked about this equation at the end of the last lecture, I made it sound like it was, I think, maybe a little harder than it actually is. It's actually easy. It's just right. It just is literally does just follow from this size of the set is the size of all of the orbits added together. Okay, so what we'd like to do over the next couple days is apply this to groups of prime power order. So now let's suppose. So let's consider the kind of first easy applications, and then we'll get to some deeper ones, which are known as the Sylla theorems in a little bit. But so now let G, the order of G, be P to the n, where n is bigger than or equal 1, and P is prime. And before going on, let me say that we know already that groups of prime order are special, right? We know that for each prime number, there's one and only one group that has that order, and it's a cyclic group of order P, right? So we know that groups of size P, where P is a prime, are like very easy to classify and very special groups. Or these cyclic groups of order P are really nice, as we know. It makes sense to study, instead of P, what if you have P squared, P cubed, right? It kind of makes sense to think that, well, these groups of prime power order are probably also interesting and nice. So in fact, there's a name for them, which is P groups. So let me say that a finite group which has order a power of a prime number is called a P group. So you can talk about 2 groups, 3 groups, 5 groups, etc. So that's just a piece of notation that's commonly used. So it is special to have prime power order for sure. So let's start to investigate why. Okay, so the first little lemma here is that, so lemma, let G be a P group. So remember that means order of G is P to the n. And the center of G is not equal to E. Right? So usually, if I have a group that isn't abelian, its center could be very small. But for a P group, we're saying that the center is always big. The center is always strictly bigger than the identity element. Okay? So how do we prove this? So in fact, it's kind of cool. It turns out that it follows right away from the class equation. So the class equation here gives that P to the n is the size of G, is the size of the center of G, plus the sum G over cent G, where the sum ranges over, I won't say what, I said what it is in the general case, conjugacy classes of non-central elements are what this sum ranges over. So this could, if there are no non-central elements, then this sum is just 0. If there are non-central elements, okay, then it contains something. So I won't say what the sum ranges over. It only matters that it's a finite sum of terms, g divided by something. So since the centralizer of G is a subgroup of G, we see that the size of the centralizer of G is p to the r for r less than or equal to n. For any element, that looks like n less than or equal to n, for any element G and G. Right? In other words, what am I saying here? The centralizer of G is a subgroup. Its size, whatever it is, divides the size of big G. What are the divisors of a prime power? They're other prime powers. Right? So this is just by elementary arithmetic. And so we see that each G mod cent G is also a prime power. This is p to the n over p to the r. So this is p to the n minus r, also a prime power. Right? So we conclude that p to the n is the size of the center of G plus some term, which is a sum of prime powers. Right? So sum of, I don't just want to write the equation again. Let's call it p to the n minus r I. Sum over some indexing set I, where now I indexes these conjugacy classes that I don't want to write out names for. Okay, so this term is divisible by p. So this is divisible by p. And this being p to the n is also divisible by p. Right? So, right, this is the sum of prime powers, so p divides into it, certainly. Oh, incidentally, maybe it's worth saying, why aren't there any ones in this sum? How come none of these numbers are 1? You might say to yourself, well, wait, 1 is a prime power. I could have p to the 0. If the size was 1, that would mean that G divided by centralizer of G would be 1, which would mean that the centralizer of G would be all of G. So, if cent G equals all of G for some G, that precisely implies that G is in the center. With the if, actually. Right? So when is this quotient equal to 1, G mod cent G? It means that the centralizer is all of G. But that just means your central element. Right? It means that every element of the group, when I conjugate by it, I get the same G. That means that GH is HG. Right? So since this sum is over things that aren't in the center, well, none of these numbers are 1. So, so that justifies this remark that all of these are positive prime powers. This is divisible by p. This is divisible by p because by assumption it's p to the n. And so what do we conclude? So we conclude that therefore the size, and this should be size, the size of the center of G is divisible by p. Okay. But also the size of the center of G isn't 0. Because the center of G always contains the identity element. It's at least, so the size is at least 1. So since the size of the center of G is greater than or equal to 1, right? It's a set that's non-empty because there's an identity element is in the center. We get that, in fact, the size of the center of G is at least p, right? I'm divisible by p, either I'm 0 or I'm p times some positive number, right? So the size of the center of G is at least p, so it's actually a stronger statement. So this certainly implies that the center of G is not the identity. Right? So in fact, I could have given you a stronger statement. Not only is the center not the identity, it's actually a abelian group of prime power order, right? Because it's a subgroup of G. Right. So whose size is in particular p to the something. So greater than or equal to p. Okay. So that's pretty cool. That's good. So what can we get from this? We can get a lot of nice things. So let's start by looking at the case. Goodman likes these concrete kind of examples, and I think he's right to do so. So let's look at the case where n equals 2. So there's a general theory here, but let's digress. Let's specialize to a moment for n equals 2. So for a moment, set n equal 2, i.e. order of G is p squared, and then there's a theorem which reads, if order of G is p squared, that implies that it implies G is abelian, basically. Either G is isomorphic to Z mod p squared, or G is isomorphic to Z mod P cross Z mod P. Right? So in other words, it's clear that any abelian group of order, so just by the classification of finite abelian groups, any abelian group of order P squared is one of these forms, right? You can read that off the elementary derivative decomposition very easily, but this is saying that no, in fact, any group of order P squared is like this. So in particular, they're all abelian. Okay, so that's not obvious, right? Like, it's easy to prove that any group of order P is abelian, but now this is saying that any group of order P squared is abelian. So already telling you that groups of prime power order are pretty interesting and surprising. So let's prove it. So so you have two options, right? So that we want to show that either it's cyclic group of order P squared or it's this product. So let's suppose G is not cyclic. Okay, so, all right, so what does that mean? That means that there's not an element of order P squared, because if there's an element of order P squared and the whole order of the group is P squared, well then, that would have to mean that the cyclic group generated by that element is the whole thing, right? It's a subset of size P squared in the set of size P squared. So, so this immediately implies that every element has order, no element has order P squared. So this implies that no element has order P squared. And since the order of an element, no element of G, maybe it's better to say, since the order of an element always divides the order of the group, right? Because an element generates a cyclic subgroup, and any order of any subgroup divides the order of the group. That means that the order of any element of this inside this group is either 1 or P. So this implies that, just to rephrase that slightly, any G in G, which is not the identity, has order precisely P. Right? You have three options, 1P and P squared. Order 1 means you're the identity, right? You to the first power are the identity. You are the identity. There's only one of those. That's it. Done. Or you're not the identity, in which case your order must therefore be precisely P. Okay? Now, the previous lemma, or proposition, or whatever we called it, says that the center of G has non-identity elements. So since center of G is not equal to E, right? It contains elements not just the identity, we can choose G in center of G, G not equal E, and then this implies, and therefore the order of G is exactly little p, okay? So if you take any non-zero element of the, non-identity element of the center, then you get an element, a central element of G, which has order P, okay? So now, so that's, right, so what are we trying to show? We're trying to show it's Z mod P cross Z mod P. So that's going to generate one copy of Z mod P, and now we need like another copy of Z mod P in there to find that, so to get this isomorphism. So now we say let H be in G minus the group generated by G. Well, we can do that because the group generated by G has order P, right? The order of G is P, and the order of big G is P squared. So the thing on the left, the set on the left, has strictly more elements than this subset, and so by counting, there must be something in the one set minus the other, and so we pick it. And so then the point is that H also is a cyclic group of order P. So then H is also cyclic of order P, because remember, any non-identity element has order exactly P by the assumption of order P squared, right? So it's kind of cool. So so now the claim is precisely that claim, that G is actually isomorphic to the subgroup generated by G cross the subgroup generated by H. Right, so I have a pair of subgroups, and the claim is that in fact their product, that the whole group is actually just their product. So how do you show something like this? So you have to show that these two groups that they commute with one another inside big G, and that anything in big G is uniquely a product of something in here and something in here, right? So that's the idea. So the first thing to show is that they, right, because if they don't commute, then, right, being a product means anything in here, right, something in here, comma, identity, and then identity, comma, something in here will always commute with each other, right? So if you're a product, that means that if you take the subgroup represented by the first factor, and the subgroup represented by the second factor have to commute with one another, right? So that's it's just a basic thing about the construction of products, is that you end up with these commuting subgroups. I don't know if I've said that explicitly in a lecture yet, so I thought I'd mention it. Okay, so the first thing we claim is that these two subgroups commute. But remember that this little g is central. So since little g is central, this commuting thing actually turns out to be, I'm spending a lot of time talking about it because it's an interesting point, but it actually turns out to be not a problem. So since G is in the center of G, we get GH is HG. And this implies, so maybe it's worth saying a little bit about this argument. So this actually implies that G to the R, H to the J is H to the J, G to the R for all R, J. Right? So in fact, not only is it the case that the two elements commute, but all their powers commute. Right? And this is a quick induction on R and J. Right? If R is equal to 1, this is saying that G commutes with any power of H. Okay, but G commutes with H. So if I keep piling on the powers of H and then moving G past them inductively, you can conclude that. And then you do an induction on R to show that all these that all the powers of G commute with H to the J. Right? So this is induction. So let me note that it really does, I mean, this is like some completely formal inductive consequence of this. Okay, so these two groups commute with each other, and so to get this product, so the claim is that every element in capital G can be written uniquely as in this form, as G to the R times H to the J. So we get a map. So let's break it down a little bit more. You get a map from this product of cyclic groups G, to make sure I'm not screwing the lighting here, sorry guys, cross, maybe it's a lamp on here in the background that maybe is actually not necessary in the daylight. That, hopefully that helps. Cross H. So you get a map, excuse me, from G cross H to big G. And what is the map doing? So if an element here is G to the R, an element here is H to the J, right? And now I'm mapping that to G to the R, H to the J, right? And because these two things commute inside big G, this is well defined. Right, so that's just a little something to check, but it's not hard to do. If I have two commuting elements, two commuting subgroups more generally, then I can always take a map. I can always take a map like this. Okay, two commuting, and these are abelian groups, so it's really easy to check in this case. Okay, so this is a well-defined map group. So I just said is well-defined. Maybe I should say more precisely, is a well-defined homomorphism. Right? And now we claim that this is injective and surjective. Remember, these two groups have the same size. Both sets have size p squared, right? This is something of order p cross something of order p, and this by assumption has order p squared. So to show that it's a bijection, I just need to show that it's either into or onto. So we're going to show into. So to show this is an isomorphism, to show iso, I'll say since size G is size G cross H, enough to show into. So it's enough to show this is one-to-one. Okay, now what does it mean for it to be one-to-one? It means, so exactly that, if I look in the kernel of the map, is the identity. So this is if and only if G to the R, H to the J is E. So maybe I'll say this way. So to see this, we claim the following. We claim G to the R, H to the J is E, if and only if G to the R is E. Right? In other words, you have two product of groups, and I want to say that the only thing that gets to the identity element is identity, comma, identity. Right? So this is just a rewriting of that statement again. And so to see that, right, so G to the R, H to the J is E, okay. G to the R, H to the J is E. That's if and only if G to the R equals H to the minus J, right? And so we just need to show that G intersect H is E, right? So what do we need to show? This is a power of G. This is a power of H, right? H is an element of finite order, so H to the minus J, that's actually just H to the P minus. So this is, remind you that this is an element of finite order, so no problem with the negative. That's H to the P minus J. So you just need to show that the intersection of these two groups inside G is actually just E. Once you've done that, then then this equality forces G to the R as E is H to the minus J, which is the inverse of H to the J. So that forces this equation, and then we win, right? So to see this one-to-one property, that actually just boils down to showing this, right? But remember that we picked H in big G, right? But H is in big G minus G, right? So if let's call it K lives inside G intersect H, right? If this is an element in the intersection, then it generates a subgroup, which, yeah, so maybe the way to say it is this. Suppose K is in here. Okay, it's an element of the group, and it generates a subgroup, which is either identity, or either K is just the identity, or is some non-identity group, right? So if K is in here, then group generated by K is contained in G, and group generated by K is contained in H. Okay, but the group generated by K, the order of the group generated by K is either 1 or P. Why? Because it divides P squared, and it's contained in something of order less than or equal P. So, right, all the orders of all subgroups are either 1P, P squared. If I'm contained in some proper subgroup, my order is either 1 or P. So the order of K is either 1 or P. The order of K is P. That would be saying that the group generated by K is the group generated by G. And then and group generated by K is group generated by H, because those both have order P, right? So if this is order P, then it's living inside this thing of order P, it's living inside this thing of order P, and that would imply that H is in the group generated by G, and that is a contradiction, right? That contradicts exactly how we chose H, right? So if this thing were to have order P, you would force H and G. Not only do they intersect non-trivially, but they're actually equal. And we chose H to exactly force that not to happen. So that's a contradiction. What did we contradict? We contradict the idea that the order of the group generated by K is P. And so, in other words, this tells us that the order of the group generated by K is 1, because it was either 1 or P. And so now that implies that K is E. Right? So what's the upshot? We took a random element inside the group generated by G and the group generated by H, any old element, and we forced it subgroup to have order 1. In other words, we forced it to be the identity. So that's exactly saying this funny thing, that the intersection between G and H is E, and so therefore the map is actually into, it's a map between sets of size P squared, it's 1 to 1, that's a bijection, and so we win. Okay. So it's a fairly sophisticated argument. It's probably maybe the first kind of interesting argument in group theory. Yeah, that's an exaggeration. We've seen a lot of interesting arguments in abelian group theory, but this is an argument about arbitrary finite groups. Okay, so we're gonna do one or two more nice corollaries for today's lecture, small lecture, and then we're gonna stop. So let's return to the general. It's a nice theorem that we just proved. I like it a great deal. So let's return to the general case of a P group. Order G is P to the N. And let's bring out a few more consequences of these identity elements. Okay, so theorem. Yeah. So I'll state it the way Goodman states it. So so G has order P to the N, right? So the theorem reads that G admits G admits a normal subgroup N. So let's recall what this means. We've talked about it a little. What's a normal subgroup? A normal subgroup is one such that if I take any element in little g and I conjugate big N by it, that is contained in N. So it admits a subgroup which is invariant under this conjugation action, right? This conjugation is an action of the group on itself, and so being normal is a subset that is invariant under that. In the world of abelian groups, we never talk much about this because it's trivially satisfied. But for non-abelian groups, it's a very interesting condition that turns out to be very natural to consider. So, so we'll start seeing it more and more now. Anyway, okay. So G admits a normal subgroup N, so that, okay, it admits a normal subgroup. Yeah, obviously it admits the whole, identity, right? Like you could come up with trivial examples of the normal subgroups, but such that E is not the identity and E is not G. Right, so there are two obvious normal subgroups, the identity and G. It's saying, no, if you have a P group, you admit a non-trivial one in there. And such that if N prime in N is any subgroup of N, then N prime is normal in G. So not only is it normal, but all of its subgroups are also normal. So, so this is saying that there's some really nice, for any P group, you can cut it, you can take this group G and you can kind of cut it in the middle by some very nice subgroup. That it's normal, it's closed under conjugation, all of its subgroups are normal in G, and well, in a minute we'll talk about considering the quotient. So maybe before I prove this theorem, let me make a quick remark about normal subgroups. So why are normal subgroups important? Well, they're important for several, a bunch of reasons, but here's one of the basic facts that we haven't discussed yet. Let G be a group and N in G a normal subgroup. Then G mod N is a group. What do I mean by that? I mean, i.e., if G, so if, yeah, maybe that's fine. G1 bar and G2 bar are conjugacy classes. Right, so in other words, what is G mod N? Is a set of conjugacy classes of G under multiplication, I guess it doesn't matter, left multiplication by N. So if G1 and G2 are conjugacy classes in G mod N, then G1, this binary operation, G1 times G2 is G1, G2 bar, is a multiplication on G mod N. Right? Okay, and why is it true? I can just tell you, because what are these G1 bar? All right, G1 bar is G1 times N. It's all of the things that are this element G1 times anything in N. And G2 bar is G2 times N. And so G1N times G2N. Okay, so you're saying this is some crazy product. What is it? Well, in fact, it's exactly G1, G2, G2 inverse N, G2, N, right? So if any element that can be written as a product, G1 times something in N times G2 times something in N, can also be written as a product this way. Why? Because I've just multiplied by G2 and G2 inverse. But this is contained in N. So this thing is equal actually to G1, G2, n. Right? This is a product of two things in n, and n is a subgroup. So the set of all things of this form is actually just G1, G2n. So when I take this conjugacy class and I multiply it by this conjugacy class, I get another conjugacy class. And so the upshot is that this thing inherits, quote unquote, is a group. It inherits the structure of a group from G. Okay? So these normal subgroups are very significant, right? Because they allow us to when we take the quotient, we get another thing that's also a group. Okay, let me prove the corollary and then, or the, what do I call this? I call this theorem? I call it the theorem. Let me prove the theorem and then we'll stop this lecture, and then next time, in a day or two, we'll go on and start to get some of the harder consequences, pseudo-type consequences. So, okay, so there are two cases here. Either, G is abelian or if it isn't abelian. So if G is not abelian, then the center of G is strictly contained in G, and it strictly contains E by our previous discussion. Or the center of any P group is not just the identity element. And so then we can set n equals Z of G. So set n equals Z. Right? Because clearly the center is a normal subgroup. Right? It's a subgroup, you can multiply elements in it, and conjugating does nothing, because if I conjugate by something in the center commutes past anything. And so that conjugation does not do anything. And so clearly it's a normal subgroup that is strictly contained between E and G, and all of its subgroups are normal because all of its subgroups are also central. So it's like immediate. I'm just going to put check mark. It's like immediate that this satisfies the proposition. Okay, so if it's not abelian, then you win. If G is abelian, okay, then the proposition is also easy because we know everything about finite abelian groups, right? So you just, right, so the point is every subgroup is normal, so normal is just nothing in that case. And then the point is that you can just pick a proper subgroup, right? So just by the classification of finite abelian groups, you can just pick a proper subgroup of this thing. Oh, by the way, now that I'm proving the theorem, I'm realizing the statement of the theorem is not quite correct. So I just said G admits it. So I have to put in that n is bigger than 1 in the statement of the theorem. If I hadn't included that, then G would be a cyclic group of order P, and then it doesn't admit any non-trivial subgroups. So even proving the theorem, so if G is abelian, then this is easy. So just by classification of abelian groups, of finite abelian groups, you can write G as a product of cyclic groups, right? Z mod P to the S1 cross Z mod P to the SL, right? And clearly all of these things have proper subgroups. Either these SIs are all 1, and then you can just take a proper subgroup in the product, or some of the SIs are bigger than 1, and then a cyclic group of a prime power order clearly has a proper subgroup. For instance, the subgroup generated by P, right? So I'll just say, just take a proper subgroup. So it's just obvious from our general knowledge of abelian groups, and if it's not obvious to you, you should think about why, that you can just take a proper subgroup of a group that looks like this in the situation where n is bigger than 1, right? So this covers the non-abelian case, this covers the abelian case, and so that's all the cases and we win. Okay, I'll stop this video now, and next time we'll start getting into some of the heavier corollaries of this stuff.